My name is Natalia Chubarova, and I represent, I'm from the Faculty of Geography of Moscow State University, and today I will present you the lecture concerning the aerosol cloud radiation interaction. And the outline of my presentation is on several mm, important points concerning solar radiation, and I will tell you very briefly about main metrics with a description of its interaction with the medium. Aerosol and cloud main characteristics, mechanism of direct and indirect aerosol effects, some examples of their effect, direct and indirect. And the last topic is just the example of our new results concerning the indirect effects of cloud aerosol interaction during lockdown COVID-19 in Moscow due to these processes. So I hope that you know that solar radiation spectrum can be approximated by the Planck equation of the black body, and here is the very famous equation from which you can see that we have the dependence of the intensity of the radiation only at the given wavelength only on temperature. And if we use the solar temperatures, the photosphere, we can receive these spectral dependence of the solar intensity just which coming to the Earth. And on the right upper slide, you see the solar spectrum with the several absorption lines due to different gas species such as oxygen, ozone, water vapor, and some other gases like, for example, the greenhouse gases as CO2. So this is quite important, and you see that the maximum of the intensity of the irradiance we have in the visible part of spectrum due to the very, very high temperatures of the sun. And what happens with these solar irradiance in the atmosphere? It has a lot of interaction with the particles, and we will speak today about mainly about the particle interaction, which include the reflection, the just the process of the diffraction, absorption, some other interest emission, and some other more complicated processes. But we today will speak about mainly the most important processes like the scattering, absorption, and transmission of solar irradiance in the atmosphere. And for the description, for the metric of these processes, we can use the volume absorption, scattering, and extinction coefficients, which are just here's the very simple equation, which we can describe the total extinction coefficient as a sum of the scattering and absorption coefficient for a given wavelength. But when we are speaking about the scattering, the scattering is the one of the most important and complicated processes in the atmosphere due to its very different and different effectivity depending on many optical and microphysical properties of the medium. So to use the most convenient characteristics, we can use this parameter x, which can be which is equal to the ratio between the radius of the particle 2p, and r is the radius, and wavelength. And depending on the value of this parameter, we can use different approaches for description of different processes. For example, if this parameter is very small, so is smaller than 10 minus 3, when the power is minus 3, we can neglect process of scattering in our medium. If we have this parameter within the interval of -3 and -1, we can use the simplified scattering theory, like relay theory. And if this ratio is higher, up to 50, we need to use the quite complicated theory, MEF theory, for the spherical particles, which has been developed, which need a lot of the computation. And for the theory, for the larger values, we can use the approach of the geometric optics. And just look at the same parameter, but in a picture which is represent you the dependence, the plot when you see the radius versus wavelengths. For different, on the right hand, you see different names of the real particles in the atmosphere, like air molecules, smoke, cloud droplets, drizzle, and raindrops. So, of course, they depend on the radius. And here you see different spectral regions, and solar radiation is just to the left hand. So you see that we need to use, when we are analyzing solar radiation, for the larger large interval of the radius, for the smoke, dust, aerosol particles, and cloud particles. The MEF theory is mainly necessary to be used in description of the processes. And this is very important because in this diapason of the particle diameter from the 10 with the power power of -1 to 10 with power of 1, we have the most important radiative process in the atmosphere, which are these particles influence on these processes. So here is the main matrix which is used for the description and for the modeling. Just as the optical thickness or optical depth in some notation. Here is the integral of the volume extinction coefficient within the heights of from Z1 to Z2. A single scattering albedo, which characterizes the absorption properties of the medium. Here this is the ratio of the scattering to the extinction coefficient, and a phase function, which describes the features of the importance of different direction in scattering. So depending on the x value, it can be just symmetric. Just here is the point of this is our particle, this is the incident beam, and you see this is all direction for to the forward and backward are just the same. And if we have the increase in x parameter, with the increase of this parameter, we have much more high importance of the forward peak of scattering. And asymmetry parameter is just the characteristics of the phase function, just using some evaluation using the with the multiplication on cosine of the scattering angle. If we look at the process of the medium, we just see that if we have the incident intensity of I at a given wavelength over the medium with the this distance ds, we have the change in this intensity, just this intensity while going through this medium, and will receive this di additional intensity, which can be with the minus or plus sign. And for attenuation, we have, for example, this classical Beer-Lambert law equation in a differential form, which can be seen. You see here that we have the direct dependence of this change in our intensity. This is proportion to this value is proportional to the incident intensity of the ds, and with the coefficient of the proportionality of the extinction coefficient. And for emission, we have the plus sign, and instead of the intensity of the initial intensity, we have the function, emission function, which is just shown here with the J letter, and just with the same coefficient of the extinction coefficient here. And if we have in our medium both emission and absorption properties, we can write our equation in the following form, and this is the most simple way how we can show you the radiative transfer equation in the differential form. So just is the sum of both terms, the emission and attenuation form. So as you can see from this equation, you see the extinction coefficient, which is necessary to know if we can use this equation in our computation. And of course, for different particles, aerosol or cloud particles, we have a very large very large parameter different in these parameters, which we'll need to know. And just speak about the parameter which we are interested in the analysis, the aerosol and cloudiness. Aerosol, atmospheric aerosol, just a suspension of small particles in the atmosphere with the diameter of the from 1 nanometer to just the 100 microns. And here is the electron microscope views of different aerosols, and you see here that it can be of different shapes and of different origins. For example, you see here the marine aerosol, the sulfate, the organic aerosol like bacteria, soot, which is a very small, which has very small size, sea salt particles, flash, and some others. And we need just to know their microphysical characters like size distribution. We need to know optical properties, refractive index, imaginary and real part of this refractive index, for obtaining the radiative properties which were mentioned above. So the spectral aerosol optical thickness, the single scattering albedo, and phase function. Here is another picture of the aerosols, but here is they are divided into the standard classification of the aerosol, which contain of the nucleation, Aitken accumulation, and cause mode. And concerning the particle distribution, we can use several metrics. We can use number distribution of the particles, or we can use volume distribution, in which instead of the number of particles, we use the volume of the particles. And in this case, you see the shape of this distribution is for the same for the same number of particles. We have quite different visualization of these distribution. Here is also just the pictures of different aerosols of different origins, both from the natural sources. You see here, this is the eruption of the volcanoes. This is sea salt, marine aerosols, for example. This is the very pronounced haze of cities, mineral salts, just the black carbon aerosol, and so forth. And here is just the example for our Moscow conditions. How can we have these so different conditions only due to the aerosol? On the right hand, you see the typical urban aerosol in Moscow, and on the left hand, it's the phenomenon which was observed in 2002 during the smoke advection air over the Moscow area, and you see that visibility is close to zero in this case. Depending on its origin, we can divide the aerosol on primary or secondary aerosol. And just the primary aerosol, just it's the what is just we have from the emission directly from the wind blown particle debris, soil erosion, volcano, sea spray, combustion, so on. And if we have the formation of the aerosol from gas particle partitioning or nucleation, gas phase oxidation, so this is the mechanism of the secondary aerosol formation. And this is a very famous picture which just demonstrates you the process of the nucleation and condensation of aerosol in the air, the process of scavenging or evaporation, and their sedimentation, just the dry deposition or washout from the rain processes. So if we look at the number distribution of particles for the different modes, and just analyzing the changing of these processes, we can say that for the accumulation of fine aerosol mode, we mainly have the secondary aerosol process of the impact of the secondary aerosol. And for the cause model, we have the primary aerosol from the emissions. But of course, for the accumulation, what we have, of course, is the primary aerosol as well. So the aerosol distributions are determined by source, processes, chemical and physical, and removing conditions. Here is the emissions of direct emissions or just the production of aerosol of different origin within the atmosphere. And we can see here that, for example, over the northern and the southern hemisphere, the effect of the natural aerosol, like sea salt or mineral dust, is the prevailing. Of course, it's very, very high emissions of these aerosol. However, we have, if we speak about the combustion of fossil fuel, biomass burning, which is also a very large particle emission in the atmosphere, and especially for the fossil fuel in the northern hemisphere. Speaking about the secondary aerosol like sulfates, nitrates, or organic, we also see that we have the, especially for sulfates and nitrates, the prevailing of the anthropogenic emission of the aerosol of this origin, especially in the northern hemisphere. And just returning to the efficiency of radiative processes. So we see that if this is the interval of the particle diameter of the aerosol, and which we are speaking about, which have a very high efficiency of the scattering. So you see, this is the normalized scattering coefficient per particle divided by the particle volume, plotted as a function of a diameter, and we have this is an efficiency of higher than 10 in this interval of the particle diameter, which is devoted to the aerosol. Speaking about the global distribution of the aerosol, we will use the metric of the aerosol optical thickness and use the most famous, just the data both from the satellites measurements, it's the data of the moderate resolution imaging spectrometer, both with the results of the modeling from the European Center for Medium Range Weather Forecasts. And you see here is the very noticeable just the places where we have a very high optical thickness. This concerns the optical thickness of the Southeastern Asia. This is the due to the anthropogenic origin. This is the north part of the India, and just also is due to the industrial development of the very high emissions of the anthropogenic aerosol, and the elevated values of Africa. This is due to the biomass burning of the agricultural debris. Yes, this is the points, and of course over Sahara. This is the mineral aerosol, which is formed just over Sahara and below over the territory of the Atlantic Ocean. Here is this is the part of this mineral aerosol as well. However, we have some other features, and the yet the variability of aerosol properties can be very, very large, and the local effects of aerosol, even in Europe or in other countries, can be very, very significant. Just speaking very briefly about cloudness, and cloud is the aqueous aerosol suspended in the atmosphere with the particle sizes from zero point 0.5 to 1000 microns, and it is characterized like non-aqueous aerosol by a very pronounced, very complex spatial structure, which can be clearly seen from these pictures. So we need, in addition to the optical properties of the properties, microphysical, we need these characteristics of the distribution of these parameters. And here is some characteristic of cloudness, cloud fraction over the whole world. So with the just shown by the red is shown the high fraction, and by the blue color low cloud fraction. Here is also the average distribution from south to the north, the liquid water path, the characteristic which is characterize how much the condensed liquid water have our cloudness, and the ice water path. Here is, you see, in the atmosphere, and also the occurrence of cloudness can be at different heights, and you see the distribution again from south to the north of the liquid and ice cloud occurrence. You see the most pronounced ice cloud occurrence of tropical zone. But for our study of aerosol cloud interaction, we'll need to focus on specific properties on the cloud condensation nuclei, so-called CCNs, which are small particles, typically of smaller than 0.2 micrometers, on water vapor condense. It's a very important part of the physics in cloudness for just description of the processes. So here is the scheme of the typical cloud droplets with the radius of about 10 micron. This is large cloud droplets with the 50 micron, and you see that the concentration of them is dropped significantly, and this is the typical raindrop with the radius of 1000 microns. So the CCNs consist of a mixture of soluble and insoluble components, and the bulk hydroscopicity parameter introduced as a concise measure of how effectively an aerosol particle acts as a CCN. So with the increase of the particle size, more active process of its wetting by water taken place, and this is in turn lead to the decrease in supersaturation in cloudness, at which the particle can serve as a CCN. So this is quite important to have this information for the description of the processes. And this is the famous Euler diagram in which you see the two liquid particles, droplets containing fixed masses of salt or ammonia. And you see here is the point of so-called stable equilibrium, and after the extremum, after the, for example, for curve 2, this is the point of the extremum, we have so-called activated pair particle, in which we have the increase in this interval, we have the increase in droplet radius with the even smaller supersaturation regime. What is important for us, speaking about the aerosol and cloud interaction, that we have at the same supersaturation region we have in different air, we have different air mass, we have quite different numbers of cloud condensation nuclei. For example, this change from this is a logarithmical change from the thousands to the tenth of cloud condensation nuclei. And the most effective cloud condensation nuclei are soluble part, and especially the sulfate aerosol. So from the natural sources, this is the dimethyl sulfate, for example, and the organic sulfur and methane sulfonic acid, which is noted by the MSA. And what is very important that we have, for example, for the marine air mass and for the continental air mass, we have the quite different distribution of the droplet concentration. We have a very, very small interval of the droplet concentration for marine and large for the continental compared with the each other. And as in addition, we have the difference in droplet radius. So this happens, we have much smaller droplet radius in continental air compared with the marine air. The effective radius is much smaller. So this is very important to remember if we're speaking about the penetration and the indirect effect of the aerosol on cloudness and as the result as well. So just a few words about the interaction between the effect. We have the both on aerosol effect of different origin. We have the scattering and absorption effect. Absorption lead to the warming and scattering to the net cooling. If we look at the just the same scheme, but we have the some processes, chemical processes of the gas phase formation of aerosol, condensed phase effect of the aerosol processes, formation and coagulation, and this may provide the so-called direct effect, which is named as air-Fari, aerosol radiation interaction, and so-called due to the if we are speaking about the indirect effect, we can just the will named is as air phase. So here's the aerosol cloud interaction, and so we will indirect effect is just the one of the is very close to the notation of air phase. And here is just the examples of the scattering and absorbing properties in different phase, which may lead to the cooling or warming atmosphere. And just very, very briefly on the direct radiative effect of aerosol and cloudness. So the most simple of it is just the change of the solar irradiance at ground level in clear sky condition and different aerosol optical thickness. You see that we have much difference in Q at 0.1 or 0.5 aerosol optical thickness. And if we just look at the loss of the solar irradiance as a function of the aerosol optical thickness, we can see the nonlinear dependence on these parameter, and which is differ for different spectral regions. Speaking about the radiative effect of the aerosol, which is the difference of the net radiation of in aerosol atmosphere minus net radiation of in no aerosol atmosphere at the top of the atmosphere. So we can obtain the following dependence of this RFE value as a function of the aerosol optical thickness, and you see in far conditions, this is the red points, we have very large negative radiative forcing effect. But it depends on surface conditions, and if you have the bright surface, for example, with the albedo of higher than 0.55, we have the much, even the positive values of the radiative forcing effects. Here is the example of the industrial aerosol in the atmosphere, which can be calculated using the chemical transport model. And you see here the just changing during the daytime of this aerosol, which is quite in a good agreement with the MODIS cloudness. As you see that the maximum of aerosol is see, not in the central, for example, of the city when we have the production of the emission of gases, but to the just in the direction with the of the with the wind direction. Yes, this is the shifting to the southeastern part of the Moscow area, for example, in this point. So one of the most important climatic characteristics of these parameters is the effective radiative forcing, which is the difference of the net radiation at the top of the atmosphere with the counting of this gas or aerosol minus this value in the pre-industrial period. And just I would just only focus on the aerosol, and this is in this scheme is this is part which I show you by the row, and you see the the mainly negative effect of the result, but a very large uncertainty of it. Here is just how this air-fari effect, so the direct aerosol effect at the top of the atmosphere, change at different latitudes. So this is only the anthropogenic aerosol effect. So that's why this is quite small in value. And speaking about the cloudness, about their direct effect, we can use several metrics. We can use the radiative transmission, which is the ratio of the radiation in cloudy, overcast clouded to the clear sky conditions. And you see that this parameter has a very nonlinear dependence on the cloud optical thickness. In addition, we have the amount of cloudness, which also play a very important role and also have a very nonlinear dependence of on cloud amount of low layer cloudness. Speaking about cloud radiative effect, it's also the difference between the net radiation cloud and no cloud conditions, and it can be of different sign depending on the surface, mainly for the shortwave radiation, like it's shown in the next slide. It's the negative, and global mean is about minus 47 watt per square meters. For long wave irradiance, it is the positives due to the absorption by the water vapor and some greenhouses processes, so it's about 26 watt, but net effect is negative due to the cloudness. Speaking about indirect cloud and aerosol effect on solar radiation, we should mention several processes. We should mention so-called Tuome effect, which is due to the seeding by the aerosol of the cloudness. We have the increased as cloud albedo, and this is the fact is with the same liquid water content, but we have another process in the atmosphere like Albrecht effect, for example, with the increasing of life of the cloudness, or just increasing the height of the cloud, or suppression of drizzle, increasing the water content couple. So we have a very large different processes taking part part in the cloud after the cloud aerosol interaction in the atmosphere. So this is the just example of how the emission from the at sea, yes, we have a very large droplet concentration with a smaller effective radius, and you see here this is the just the decrease in effective radius, just provide us the increase of the concentration of these cloud droplets number concentration over this the same area. And if we look from the space, we have in these areas so-called these crabbles, which is shown due to the ship's routes. Also, there is a correlation of the cloud and aerosol microphysical parameters, like it's shown from these areas. So we have the larger effective radius of oceans and smaller of continents due to the continental much more high concentration of aerosol over continents. And speaking about the both RE direct and RC non-indirect cloud aerosol interaction, we have different estimates from different chemical climate mode from different modeling group, which are shown on the left side. This is the just information from the IPCC 1213, and you see that the ensemble mean of this value is minus 1.08 watt per square meters, but it differ for different in a very large scale. According to the recent IPCC, we can just obtain that the direct aerosol radiation interaction have the minus 0.27 watt per square meters. The non-direct effect is the quite large. It's minus 0.96 watt per square meters. In total, we have minus 1.23 watt per square meters if compared with the CO2 effect of plus 2.69. So you see this is comparable values, and we have a very nice offset due to the aerosol, this warming due to the increase in the concentration of the CO2 during the same period. And the last topic which I would like to show you, this is the just effect, just example of the indirect effect of the aerosol cloud interaction during the lockdown in Moscow. You see, this is the period of the spring 2020, when we have really street were very empty during this lockdown period, and using satellites data, we obtained this is the number concentration of liquid droplet concentration, and just from different algorithms, and for the taking only northern advection cases for the homogeneity, we may have the comparison for the this number concentration of cloud droplets during lockdown and during the other years with the similar synoptic situations. Using this activating scheme from the Sickle-Skyen, which was just proposed in 2006, we can simulate the cloud optical thickness and radiative effect of these smaller liquid concentration of cloud condensation nuclear, which is twice as smaller than in the average value in the similar conditions. And finally, we have the very pronounced effect. We have the model simulation using mesoscale with this radiative scheme, which take into account for the indirect effect, you see we received a very pronounced effect in radiation of about 40 watt per square meters, just for the difference between the typical and lockdown concentration of our particles. So
One
the
more thing.
conclusions, yes, I'm just finished. Thank you. So just that this is a very important topics, and yet there are large uncertainty of direct aerosol cloud interaction effects on radiation, which need further studies. Thank you very